Good morning, and thank you for joining us. Today's webinar is on the Purge, how to reduce cost without reducing data quality. Jacob Rebholz is presenting today. We will be answering questions at the end of the webinar, so feel free to submit them throughout the presentation. Okay, Jake, I'll turn it over to you.
All right, thanks, Shelly. Good morning, my name is Jacob Rebholz. I am the VOC product line manager here at Teledyne Tekmar. And today we're going to be discussing Purge Gas and ways that we can reduce costs without affecting our chromatographic quality. Excuse me. Okay, so just a quick overview of what we're going to talk about today. We're going to start with the basics of using different purge gases for our various analogies. We'll cover how to select for nitrogen purge gas within the Teledyne Tekmar family of purge and trap concentrators. And then we'll look at some comparisons of data using both helium and nitrogen as a purge gas as to set our benchmark or our baseline of nitrogen as a purge gas. And then we'll finish up with some examples of full application notes of two standard EPA methods using nitrogen as the purge gas. Okay, but first and foremost, why are we even talking about this? Well, like many of you probably realize, recent developments in the Middle East have caused a hiccup, we'll say, in the supply of helium. Now, like many of you, I was unaware that Qatar even produced helium, let alone a third of the world's supply of helium actually does come from Qatar. And when the land border between Saudi Arabia and Qatar was shut down, that caused a complete shutdown of shipments of helium out of Qatar. They were able to quickly come up with a solution to ship out of their own port, but it's at a significantly diminished capacity over what they were doing previously. So this has caused a hiccup in the supply and may continue to cause issues with timely supply and or the cost of helium. So what can we do to either buffer ourselves against a potential shortage or simply to reduce costs in a uncertain helium world? Well, we have two main uses of helium in our purge and trap analysis. First being the carrier gas of the GC. So we could start here and we could look at alternative carrier gases. However, doing so definitely comes with some trade-offs. First and foremost, we're definitely going to see shifts in our retention time, and we may see some separation issues. Now, these two things alone may require significant method parameter changes, and this takes time. It takes time to develop methods that work efficiently with alternative gases, and then it takes time to revalidate our methods so that we can produce good quality data that will stand up to audits. More specifically, if we look at issues with hydrogen as a carrier gas, chief among it are its corrosive nature and its explosive nature. So there are certainly some safety concerns when using hydrogen as a carrier gas. We have to make sure that we don't allow concentrations to build up to explosive levels. So we need proper venting of the GC. We need to make sure that our mass spec vacuum stays good so we don't create an explosive environment within the mass spectrometer or the oven. So we need to make sure that our GC is leak tight, things of that nature. We're also going to see some BFB tuning issues because the BFB tune criteria was written around helium as the carrier gas. Additionally, with nitrogen, we're going to see some of these same issues. Nitrogen is going to generally give us poorer separation of compounds on the same columns that we would typically use with helium. So all other things considered the same, we're going to see generally poorer separation. And then again, we're going to have some BFB tune issues because those criteria were written around helium. So if changing our carrier gas is going to have these types of barriers, what's our other option? Well, our second use of helium in our analysis would be on the purge and trap side. So just looking at the typical gas use in a concentrator, it takes up to 1,200 milliliters of gas per active sample. So that includes purging, dry purging if you're using dry purge in your analysis, bake time, sample draining. Add all that up, you come up to over a liter of gas used per sample. And the case doesn't look a lot better in standby mode. You can use up to 1,200 mils per hour of gas just in standby mode. Every hour of every day that you're not running that concentrator, you're using anywhere from a half to a full liter of gas per hour, just keeping that system purged and clean and free of oxygen and other contaminants. So if we were to look at using an alternative gas, there could be significant cost savings there, right? So the obvious choice in this case would be nitrogen. Hydrogen is not, I repeat, is not an option for purge gas. And the primary reason for that is that when we go into desorb preheat, we seal off that analytical trap, and then we heat it up to 150 to 240 degrees C. And that's definitely going to create an explosive environment by pressurizing that hydrogen under heat. It's definitely going to cause a dangerous situation. So we do not want to use hydrogen. It is not an option. However, nitrogen is still an option, and it's a good option. It's relatively inexpensive. Labs can choose to use generators that are going to concentrate the nitrogen that's readily available in the air around us. And then compressed cylinders of nitrogen are much less expensive than helium, even when the helium supply is stable and abundant. So, also, nitrogen often provides us more than adequate purge efficiency for the standard EPA compounds under standard EPA parameters. So how do we switch to nitrogen as our purge gas? Well, that's really easy to do with the Tekmar purge and trap concentrators. First and foremost, this is because of our mass flow controller. So we have full independent electronic control of all the flows and all the modes, and they're all variable and independent from one another. And because we're measuring the actual mass flow of the gas, we know that we're going to deliver the right volume of gas independent of pressure in the system for the gas that you choose. And so through the software, we can actually select the gas that we want to use, and we can do fully automated leak checks to make sure our system is tight. So we get a lot of great advantages from using this mass flow controller. Additionally, when we do choose nitrogen, in the vast majority of cases, the standard purge parameters that most people are using for EPA methods, that being 40 mils per minute for 11 minutes, is going to be more than adequate with nitrogen as your purge gas. So in most cases, we need very few or even no changes to our purge and trap method. Now, with some compounds, we might see suppression of purge efficiency, and that can be overcome by purging for a longer amount of time, purging at a higher flow rate, or heating the sample to help release those compounds from the water or the soil matrix. Okay, so let's start with a couple examples looking at the Atomx, and then we'll move on to the Lumin and look at some water examples. So selecting your nitrogen purge gas in your Atomx Teklink software is very simple and straightforward. We go to Tools, Configuration, and then we choose the Options tab of the configuration window, and then we have our purge gas. It's simply a drop-down menu, and we can select helium or nitrogen. And again, like I say, that mass flow controller is calibrated for either one of those gases. So if we choose nitrogen, we know that we're going to get 40 mils per minute of nitrogen, not some equivalent that would be based off of what you would get with helium. Similarly, leak checking is very simple. There's a dedicated radio button on the main screen that's visible at all times. So you click the leak check button, you load an empty vial into position 1, and it's going to do a full leak check of the entire system. So that's going to include the needle, the vial itself, the analytical trap, condensate trap, the sparger glassware on the front of the instrument, and all associated plumbing and valving. Furthermore, if a leak is detected, the Atomx will then step down through 3 different sub-zones or sub-modes of the instrument to help you further hone in on where that leak is coming from. So it really simplifies that troubleshooting, really helps you dial in on where your leak is and get it repaired as quickly as possible so that you get back up and running as quickly as possible. Okay, so moving on into some data here, we're going to look at primarily method 8260 for the Atomx. We're going to look at some water data and some soil comparisons for purge. And in particular with the water and the soil chromatography comparisons, we're going to be looking at helium versus nitrogen as the purge gas. And all of the data that I'm showing today, all of these examples, helium will always be the carrier gas. because we want to maintain the chromatographic efficiency that we get with using helium and that data integrity that we get by not changing our GC methods and our mass spec methods. So we're going to keep all that the same. We're only modifying the purge method as necessary, which in most of these cases involves little or no changes, and then changing the outside of the actual purge gas itself, which will be nitrogen. And then we're going to look at some data here of calibrations. So calibration results, MDLs, that sort of stuff. Okay, so let's start by looking at the differences between nitrogen and helium. Just what do you see in your chromatogram? How does it look? What type of purge efficiency do you get? So looking at a water purge on the Atomx, here's the method that we used. Again, it's the same method in both cases. I'd like to highlight here that we are still using 11 minutes of purge and 40 mils per minute. Excuse me, go back. So 11 minutes of purge, 40 mils per minute flow rate. And then dry purge, again, is a very typical dry purge of a half a minute at 100 mils per minute. So 50 mils of dry purge. So very typical volumes and times and flows that we would use with helium are going to work in this case for nitrogen as well. And then again, similarly in the soil side of things, we see that we're using 40 mils per minute for 11 minutes. And then again, our dry purge is 100 mils for a minute. So again, very common purge parameters. In this case, we chose not to heat the sparge vessel for the water side because we didn't need it to get that improved purge efficiency. So let's see. And then for the GC side, again, like I mentioned, we're doing it in helium. Typical split ratio 80:1, which is going to help with some of that water management. Very run-of-the-mill GC method here. This is typical of what we'll use in all of our purge and trap methods, our application notes that we release. Okay. So here's an overlay of a 50 ppb water standard. The blue line is the helium purge chromatogram, and overlaid on top of that is red is the nitrogen purge gas. And so we see a little diminished peak size or height here for the gases. Mid-range looks pretty good. Some of the heavies maybe didn't purge quite as well. But generally, overall, we see that we have really good recovery here. And when we look at some of the data later on that was done with the nitrogen purge, we see that we still have good low-end sensitivity. So even though we may see a slight diminishment in the total amount of compound removed from the water and put on the trap, it's still, in most cases, more than adequate for us to get the sensitivity we need. And if we do need additional sensitivity, we still have all of those same parameters available to us, the same tools that we would use even with the helium purge, that being maybe a larger sample volume, higher purge flow rate, or maybe purging for a longer amount of time, and then heating that sample to help that purge efficiency. When we look on the soil side, we see that we have very similar results here. And in general, that makes sense because we tend to have slightly diminished purge efficiencies in soil mode in vial purge anyway. And so those minor differences between helium and nitrogen become less apparent. From front end all the way to back, we see that we actually have really good purge efficiency or very similar results between nitrogen and helium in the soil mode. So that's for any in-vial purge, whether you're treating your waters like an in-vial purge or you're doing actual true soil samples in the vial. So let's just look at some of the actual numbers here. We see that calibration results, so our percent RSDs and our calibrations are very similar, maybe a little tighter in helium, but again, really good results. 10% RSDs on calibrations are very good, whether we're talking in vial purge or liquid purge on the sparger, and whether we're talking about nitrogen or helium, those are good results. Similarly, we see low MDLs in both soil mode and water mode with both nitrogen and helium as our purge gases. And then we see good response factors, generally speaking, across a wide range of compounds. So this just goes to show that in most cases, nitrogen really does give us pretty decent results, right? We don't really give up a lot by making that change. Okay, so let's move on to some more specific data. So this isn't one of our application notes looking at 8260 with a nitrogen purge. And again, we can see here that for the Atomx parameters, with the exception of using nitrogen as a purge gas, we have very run-of-the-mill purge parameters, 11 minutes, 40 mils per minute, things of that nature. Moving on to the GC, in this case we used the thermo GC with the helium saver inlet, which further reduced the use of helium in this particular application. But again, our actual separation and detection is being done in helium, so we're not using any alternative carrier gas. We're just looking at using nitrogen for our purge. For our calibration results, we saw that we had excellent RSDs across all 92 compounds. So for 68 of those compounds, we were below 10% RSD on average response factors calibration. Only 4 compounds out of that entire list were done by quadratic calibration. So we had really good linearity across most compounds. And then we had excellent MDLs. We were below a half ppb for 90 of those 92 compounds and below 1.1 ppb for roughly half of those 92 compounds. So here's an example of a chromatogram that we're able to collect. I believe this is a 0.5 ppb or maybe a 1 ppb. But for the first 6 gases separated out here by their target ions, we see that we have good intensity of target ions. We have nice separation. So again, the nitrogen purge is not going to affect our chromatography. Looking at calibration results, we see good calibrations on the gases, which tend to be difficult. Light compounds, hard to purge, hard to hang on to. Water can really interfere here. So nitrogen did not have significant effect as a purge gas on the gases. Aromatics, again, we have really tight calibrations through these compounds, good average response factors, and really low MDLs. Additionally, excellent results on GROs. So regardless of what type of methodology you're running, if you're looking at a full 8260 list, if you're just looking at GROs, you're going to have good results using nitrogen as a purge gas. So in summary, for 8260 type methodologies, we have excellent recovery in the soil purge, very, very comparable to helium as the purge gas. We have good recovery in liquid, in the water mode, very comparable to what you see with helium. Maybe slightly reduced, but again, we have plenty of tools at our disposal to help increase that efficiency. We have good low-end sensitivity. We have low MDLs on all compounds, and we met all the method parameters for the calibration. So we did not struggle in meeting calibration requirements, in meeting MDL requirements, those sorts of things. All of those method parameters were met easily because, again, we did not mess with the GC. We were still using helium as a carrier gas. So let's move on to some drinking water examples now, because when we talk about maybe slightly diminished purge efficiency, some of the concern that may come to mind is, what can we reach the levels we need to see in drinking water? So for this example, we're going to look at the Lumin purge and trap concentrator. And again, real quick and easy to select our purge gas. We go to Tools, Configuration, and then we choose the Options tab of the configuration box. And then we have a drop-down menu where we can choose either helium or nitrogen. So in this case, we're going to use nitrogen. Again, leak checking has its own button here in the tools. So we can simply select leak check. It's going to do an automated leak check of the whole system and tell us if we pass or fail. Because the Lumin and the Aquatech is a much simpler system, it's going to test it all at once. But there's only going to be a handful of places where that leak could exist, primarily in your sparger, your sample loop, and your liquid transfer line between the Aquatech and the Lumin. And then last but not least, your internal standard manifold is a common area for leaks. So relatively quick and easy to troubleshoot that system as well. Get yourself leak tight, and then we're off and running. So for this example, we're going to be looking at 524.3, or more specifically, 524.4, which explicitly allows nitrogen as a purge gas only. Does not allow nitrogen as a carrier gas, but only for the purge. So we're going to use this method. Obviously, we're looking at low concentrations because it says a drinking water method. So we're expecting to have low concentration of our target compounds that we're looking for. And then again, we're going to present some calibration data from this analysis. Okay, so here are the instrument parameters we used. Again, drawing attention to 11 minutes at 40 mils per minute. We did not fine-tune this method to be fast, simply to use nitrogen to show that we could get adequate calibration results when compared to a typical helium purge. And then again, same thing on the GC side, very typical GC parameters that we would use for a variety of our application nodes when using helium as our purge gas. So here's a chromatogram of the first 6 or 7 gases here. And we're looking just at the primary target ions. But again, we see that we have adequate separation for our target ions for these gases, and we have nice peak shapes. And this was done in, I believe, a 0.5 PPB standard. So even with a somewhat potentially diminished purge efficiency, we're still seeing good recovery of our light gas compounds with minimal water interference, thanks to the new water moisture control in the Lumin. Actually, if we go back, point out that we did not use any dry purge in this method. And that's simply because with the new moisture control system of the Lumin, we were able to remove an adequate amount of water through hardware controls that we didn't need to use method controls in order to remove that water. So we still have excellent gas separation and peak shape, even without dry purge. And then here's an example of a 5 ppb standard, and we see nice peak shape, nice peak height, good separation. And again, because this is all being done in a helium environment, we're only using nitrogen as the purge gas. And we're getting adequate purging of our target compounds from the liquid and moved over to the GC. So moving on to some data, looking at some of the light compounds on the front side. Again, we see very linear results. We're getting R squareds of 3 nines, 2 nines, even 1 in many cases. We have nice low MDLs. We meet the MRL confirmation requirements. And our precision and accuracy looks very nice. And then as we move through the middle of the list, the middle eluders, again, we still see very linear results, low MDLs, and we're meeting the MRL confirmation requirements. And last but not least, looking at the back end, the heavy compounds, still very linear results, still low MDLs. So even for those heavier compounds, we're still getting good purge efficiency. So to summarize, all compounds were linear across a dynamic range. We had excellent low end sensitivity, as you would expect for a 524 series drinking water method. And we met all of the method parameters for the calibration. So the MRL requirements, the MDLs, linear calibrations, all of that was met using nitrogen as a purge gas. So to wrap things up, nitrogen is a purge gas. It is adequate for most methodologies, including the popular EPA methods. For some more specific methodologies, looking at, say, Jasmine and MIB, you might need to make some more method parameter changes there in order to be successful with nitrogen. But for your typical standard EPA methods, in many cases, it can be a simple switch from helium to nitrogen. You'll always want to confirm that with shooting some standards, and you may need to make minor adjustments to bring your data back to look where you expect it to be, but it takes significantly less effort than switching your carrier gas on your GC. And then last but not least, nitrogen is very easily configured in Tekmar purge and trap systems. All it takes is a few clicks of a button. The mass flow controller is going to be programmed for nitrogen, so you can rest assured you're getting the flow rates that you're supposed to get because it is calibrated for nitrogen. And then you still have that electronic leak checking. So whether you're using helium or nitrogen, you know you're going to get the flows you need, and you know your system's going to be leak tight. So who is nitrogen good for? Nitrogen is a good purge gas candidate for those who want to reduce operating costs, who want to buffer themselves against an uncertain helium supply, but don't want to compromise chromatographic quality or invest a lot of time and effort in developing new carrier gas methods on the GC. So if you just want a quick, easy change that you can make that takes very little time and will reduce your helium usage, nitrogen as a purge gas is a good candidate for consideration. So that wraps things up here. Thank you so much for attending, and now we're going to answer some questions. Keep in mind that all the data that I presented are available as application notes on our website, which is www.teledynetekmar.com. You can also follow us on Twitter, Facebook, and LinkedIn to get updates for when we post new webinars, new application notes, for trade shows that we're attending, all of that sort of information. And then if you ever need customer support, technical support, or questions about purchasing instruments, you can call us by our phone number or reach out to us by email or contact us through our website. So now let's move on and see if we have any questions here.